Before I get started, I'd like to give a shout out to a few different organizations and people for some of the facts and figures and resources that I used in putting this talk together. So as Brian mentioned, I would like to share a little bit about my own story before I really dive into this. And that includes growing up in a Christian home and coming to faith at an early age. My dad was an engineer, and he had a telescope that we'd take out in the backyard and look at the stars and the moon and the planets. And it was really that inspired my early interest in all things science, but particularly astronomy. And, we studied what we could see through his telescope with the understanding that God was the source behind it as a creator. And I didn't get too far along in my schooling until I encountered my first professing atheist. And it was in junior high biology class. And my teacher would go so far as to say, you might as well just leave your faith at the door, because what we're going to be talking about here in your biology class is almost certainly going to contradict what you've heard at church. And so, here I am, in junior high, 12 or 13 years old, I guess. And it just didn't make sense to me. I remember thinking, how could the truth about God's creation contradict who he is as the creator behind it all? And so I look back on that experience with a sense of fondness, actually, because of the fact that it set me on a path very early on to explore God's creation and figure out how to reconcile faith and science. So I thank you, Mr. Rydell, wherever you are. So I'm thrilled to be here with all of you. This is a unique event and a beautiful location, and what a wonderful group of people. I have to admit, and I was telling Hugh this before, I'm feeling a little bit intimidated to be talking about anything related to fine-tuning in the presence of this very distinguished gentleman in our midst, who is probably the world's foremost expert on fine-tuning. But let me just say this, you can think of my approach as fine-tuning for dummies. And before you get that wrong, I'm the dummy that I'm talking about. If I can understand it, then anybody can understand it. So this evening, I'm going to be comparing and contrasting various attributes of our neighboring planets with the goal of seeing just how life-friendly these other terrestrial planets, Mercury, Venus, and Mars, really are. Make sure I can get, there we go. So first of all, we might be tempted to think, well, all the planets in our solar system share the same star. How different can they be? And granted, our star, the sun, is the perfect size, brightness, and age for life. And it turns out that the individual planets in our solar system have some pretty important differences among them. So this evening, we'll be talking about just how Earth-friendly and life-friendly the other terrestrial planets are by comparing and contrasting some of their most important characteristics to those of the Earth. So this diagram actually shows the relative sizes of the planets out from the sun. So closest we have Mercury, then Venus, then Earth, then Mars, and then, huge Jupiter, Saturn, Uranus, Neptune, and then little Pluto out beyond the Jovians. So in his book, The Remarkable Spaceship Earth, astronomer Ron Cottrell points out 9 specific attributes of the Earth that make it habitable. And first we'll start with Earth's location, or its distance from the sun. And if the Earth were just 1% to 2% farther away from the sun, we'd have consistently icy temperatures like what we see on Mars, where the water is typically frozen. And on the other hand, if Earth's distance from the sun were just 4 to 7% smaller, the atmospheric greenhouse effect would raise surface temperatures to about 900 degrees Fahrenheit, similar to what we see on Venus. So it would be too hot for oceans or for liquid water, just as we see on both Mercury and Venus. And Mercury, by the way, has wide temperature variations between night and day, of course, depending on which side is facing toward or away from the sun, with a high of around 750 or 800 degrees Fahrenheit and a low of about minus 330 degrees Fahrenheit. So this is somewhat of an aside. How many of you have heard of the Teich's-Bode law or the Teich's-Bode rule? Okay, a smattering of people. It dates back to about 1715 AD, and it somewhat eerily predicts the positions of most of the planets in our solar system. So I know this is probably kind of hard to read, but in the second row of this table, we see the order of the planets moving outward from the sun. And in the third row, we have the distance in astronomical units for each planetary slot that's predicted by the Teich's-Bode rule. And these numbers are calculated by starting with the numerical sequence of 0, then 3, then 6, then 12, and you continue on doubling those numbers, and then adding 4 to each one of those numbers in the sequence and dividing by 10. And the fourth row gives the actual average distance from the sun that the planets are. And it's been suggested, if you can see, I know it's hard to see that in that chart, but they actually come pretty close to those slots where the actual planets are. And it's been suggested that this rule may be explained due to orbital or gravitational resonance between various solar system objects that prevent regions in between these predicted slots from supporting stable orbits. But that's a suggested explanation. But in any case, it's one more piece of evidence of the orderliness of God's creation. So after Earth's just right location, we have Earth's just right size, which gives rise to its gravity and atmosphere, and also influences its temperature. So bigger planets typically have thicker atmospheres. So think of Jupiter and the other Jovian planets with very thick atmospheres, while smaller planets typically have thinner, drier atmospheres. You think of Mercury and Mars. And in this image, you can see Earth's atmosphere viewed from space. It's been described as a thin blue line, since it appears almost insignificant next to the Earth. But our atmosphere insulates us from the extreme temperature ranges of roughly positive 250 to negative 250 degrees Fahrenheit between day and night in space. And it protects us from harmful solar and cosmic radiation. Mercury and Mars are both much smaller than the Earth, with less gravity, both having about 3/8 of Earth's gravity and very little atmosphere. And because of the fact that they have very little atmosphere, they have little to no insulation from varying day to nighttime temperatures, and little to no protection from harmful radiation, and no life-giving oxygen or water vapor. If Earth's mass and diameter were greater, Earth's core temperatures would be hotter, which would also increase surface temperatures. And Earth's gravity and atmospheric pressure would also be greater, with more of the lightweight, dangerous gases like methane and ammonia being retained. A very small increase in Earth's size would make life altogether impossible. And on the other hand, if Earth's mass and diameter were smaller, its gravity would be weaker, our atmosphere, including the essential oxygen and water vapor, would be too light to be retained, and the decreased surface temperature would result in a wasteland similar to what we see on Mars. And here's another amazing example of the fine-tuning of Earth's gravity. The deadly gases of methane, or CH4, and ammonia, or NH3, have molecular weights of 16 and 17 grams per mole, respectively. And they're fortunately a little too light to stay in our atmosphere in great quantities. But life-giving water vapor, or H2O, only slightly heavier at 18 grams per mole, is just barely heavy enough. So think about that knife's edge of between life-giving water vapor and deadly methane and ammonia. And as we know, the Earth makes a complete rotation on its axis every 24 hours. A significantly slower rotation, such as we see on Mercury and Venus, would cause longer days and nights with more extreme day and nighttime temperatures, such that the plant life that we have on planet Earth could burn up during the much longer days or freeze during the much longer nights. A faster daily rotation rate would drastically alter Earth's climate. The tropics would get warmer while the poles would get colder. And this, of course, would reduce the habitable areas on Earth and possibly bring about another ice age. So you can see from this slide the drastic difference between the rotation speed and day length of Earth as compared to Mercury and Venus. And with Mars, even though it has a slower surface rotation speed than the Earth does, due to its size, it still completes one rotation every 24 hours and 39 minutes. So Martian day is just a bit longer than ours is. Nevertheless, excuse me, human studies have shown that even this small time difference in day length can be difficult to adjust to, resulting in fatigue, irritability, low energy, and difficulty concentrating. The planet's rotation rate can also contribute to the strength of its magnetic field. So Earth's relatively fast rotation rate compared to other planets and metallic liquid core give us a relatively strong magnetic field, which protects us from the deadly solar winds. And our magnetic field protects the atmosphere by repelling charged particles from the solar wind, which might otherwise strip it away from the Earth. And another kind of interesting tidbit is that migratory animals, all the way from honeybees and butterflies, homing pigeons, tuna fish and dolphins, as well as whales, all have a substance in their brains called magnetite, which essentially acts like a compass needle, enabling them to sense the orientation of the Earth's magnetic field and make their seasonal migrations north and south. Isn't God amazing? I mean, it's just mind-boggling. And you can see from this slide that none of the other terrestrial planets have much of a magnetic field, which can be attributed to a combination of slow rotation rates, particularly for Mercury and Venus, and or solid or non-metallic core compositions. But the small amount of solar wind that creeps in through Earth's magnetic field at our north and south poles produce the auroras, or the northern and southern lights, which to me act as beautiful reminders of how our magnetic field protects us. Next, the Earth's atmosphere and its composition is perfect, with 78% nitrogen, 21% oxygen, 1% argon, and other trace gases. Either more or less of either nitrogen or oxygen would ultimately result in death. And if there were more oxygen than what we have, everything would burn or oxidize a lot faster, impacting the rate of our internal metabolic processes, making our bodies age a lot quicker. And on the other hand, too little oxygen and our cells would die from hypoxia. And as you can see here, juxtaposed with the Earth's perfect balance of nitrogen and oxygen, Mercury has a very scant atmosphere made up of just tiny amounts of hydrogen, helium, and atomic oxygen. Venus has a very thick atmosphere made up mostly of carbon dioxide, along with these insane clouds of sulfuric acid. And Mars has a thin atmosphere that's dominated by carbon dioxide. Surface atmospheric pressure across the four planets range from essentially zero on Mercury to about 1/100th of Earth's pressure on Mars, to 92 times Earth's atmospheric pressure on Venus. On both Mercury and Mars, if a person is exposed to that low of atmospheric pressure without a protective pressure suit, all of the gases dissolved in their bodily fluids would escape, literally making not just their blood, but other bodily fluids boil. Not a very friendly thought. Conversely, on Venus, that's pictured in radar here, The incredibly high atmospheric pressure has crushed the spacecraft that have landed there. So imagine what it might do to an unprotected human body. So continuing to extol the just rightness of Earth's atmosphere, the ozone layer in our stratosphere further protects us by absorbing high energy radiation from space. If there were less ozone in the stratosphere, biological life would be destroyed by the excess radiation. And if there were more ozone in the stratosphere, biological life would not receive enough of the sun's energy for photosynthesis and vitamin D synthesis. Also, the small amount of carbon dioxide in the atmosphere is just enough to hold in some heat, but not enough to create a runaway greenhouse effect. And the small amount of water vapor in our atmosphere also helps to hold in some heat, in addition to providing us with rain as a vital part of our life-giving water cycle. Any more water vapor and we get a runaway greenhouse effect. Any less water vapor and life on land suffers from meager to no rainfall. And on a related note, lightning strikes somewhere on Earth roughly once each second. Any more than that, we'd have too many grass and forest fires. Any less than that and not enough nitrogen from the atmosphere gets converted into nitrates, which are essential for plant growth. And with regard to Earth's axial tilt, the 23.5-degree tilt of Earth's north-south polar axis, as it revolves around the sun, produces seasons. And with the seasons, it actually doubles the available crop-growing land area. In comparison, Mercury has essentially no tilt. Venus is tilted so much as to be upside down, as evidenced by its backward or retrograde rotation. And similar to the Earth, Mars is tilted at about 25.2 degrees. And thanks to our special location in the solar system, our special gravity, our special atmospheric pressure and composition, Earth is the only place that we know of so far in all our exploration to have water existing in all three physical phases, solid, liquid, and gas, which is necessary to establish a water cycle and for life. Simply put, where there's water, there's life, and without water, there are wastelands. And water is a basic building block and the perfect solvent for other chemicals that are needed for life. It's probably the most important compound on Earth. Its relatively low boiling point allows it to be easily purified on an ongoing basis as part of the water cycle. And another important yet kind of bizarre property of water is that unlike most other substances, it becomes less dense when it freezes and floats on top of the liquid water, acting as an insulating blanket. And without this somewhat strange characteristic, it would act like other liquids, becoming denser and sinking as it freezes, allowing more ice to form on top of it. In that scenario, rivers, lakes, and even oceans would freeze essentially solid during the winter. And in the summer, only the top surface layer would melt. We'd have surface slush during the summer and solid ice during the winter. And biological life would be essentially impossible. Mercury is too dry and too hot on the sunny side and too cold on the dark side, and lacks enough gravity and atmospheric pressure for a water cycle. Venus is too hot and lacks water vapor. Mars is too cold and doesn't have enough gravity or atmospheric pressure to hold on to water vapor if it were to melt. If water melts on Mars, first of all, you've got this atmospheric pressure problem that would cause the water to immediately evaporate. Once it's in water vapor form, then the water vapor at 18 grams per mole is too light for Mars with 3/8 of Earth's gravity to hold on to water vapor, and it basically goes up to the top of the atmosphere and gets stripped away. So so Earth is the only terrestrial planet we know of with the perfect temperature range, gravity, and atmospheric pressure and composition to sustain a water cycle. Earth's outer geological layer, the crust, ranges from 4 miles thick in the ocean basins to 30 miles thick under some of our mountain peaks. Yet if the Earth's crust were just on average 10 feet thicker, the metallic elements within the crust would have combined with all the free oxygen available in the atmosphere, making it unavailable to support life. On the other hand, if Earth's crust were any thinner, it'd be less stable, and there'd be much more seismic and volcanic activity. And this slide shows the average crust thickness of the 4 planets, and while both Venus and Mars show signs of recent surface deformations, Earth is the only one that we know of to have tectonic plates that reshape our planet's surface features, as well as recycle elements through subduction, continental drift, earthquakes, and volcanic activity. And our moon has not only helped ancient peoples keep time through the ages, but it's also largely responsible for our ocean tides. If it were bigger or much closer, it would cause tidal waves, submerging continents on a regular basis. And if it were smaller or much further away, there'd be no tides and shoreline waters would stagnate. The moon is also just the right size to stabilize Earth's rotation axis, as well as to maintain the Earth's rotation rate. And if the Earth had more or less than one moon, our tides, daily rotation rate, and tilt would all be impacted. And Jeff spoke eloquently about eclipses, and you may remember one of the things that he said is about this uncanny coincidence that the sun is about 400 times the diameter of the moon, yet nearly 400 times as far away from us. So of course, they appear, both the sun and the moon, to be about the same size in our sky, producing these perfect solar eclipses. So I'm not going to go into more details there, but about the wonder of solar eclipses and all the neat things that can be discovered because of the fact that our moon and our sun are the same size in the sky. But I do want to show you kind of a cool thing here. So Mercury and Venus have no moons, and Mars's 2 moons are named Phobos and Deimos, or fear and panic. Instills a lot of confidence, right? While Earth's moon is a little more than 1% of Earth's mass, Mars's moons are minuscule in comparison. Phobos is less than 1/millionth of our moon's mass, or less than 1/10 of a millionth of Mars's mass. And Deimos is only 17% of Phobos's mass. So neither of these moons would be large enough to produce much of a tidal force on Mars, or Earth for that matter. This is an image taken from the surface of Mars by NASA's Perseverance rover of Phobos partially eclipsing the sun. So as you can see, Phobos is way too small to cause a total solar eclipse, but it's still a pretty cool photo. I mean, come on. And the outer planets can experience total solar eclipses more regularly due to the fact that the sun would appear substantially smaller in the sky than many of their moons. For example, Jupiter's large Galilean moons, Saturn's Titan, Uranus's Titania and Oberon, Neptune's Triton, and Pluto's moon Charon could all eclipse the sun. Actually, Hugh may be able to speak more to this in terms of, I don't believe, and I could be wrong, it may be one of the Galilean moons of Jupiter that if everything lined up just right, you might get a fairly close to perfect solar eclipse on one of the, not even? Okay, good. I was hoping that was the case, but I wasn't sure. So you've heard it from the expert, no perfect solar eclipses anywhere else in the solar system. So just to summarize these other terrestrial planets, Mercury has almost no atmosphere, has huge temperature swings from scorching days to freezing nights, low gravity, almost no magnetic field, and certainly no life-giving water cycle. And next we have Venus, Earth's so-called sister planet, just slightly smaller than the Earth and a little closer to the sun, but that's really where their similarities end. As I mentioned earlier, Venus's surface temperature is nearly 900 degrees Fahrenheit, with an atmosphere so thick with carbon dioxide that its pressure is more than 90 times that of Earth, as well as clouds laced with sulfuric acid and no water. So not a very friendly sister, if you ask me. And in the other direction from us, further from the sun, we have Mars, the red planet, and the one that I like to call the object of NASA's affection. It's substantially smaller than the Earth with very little atmosphere, and all of its water is frozen, at least most of the time. So again, there's no life-giving water cycle on Mars. So if the Earth were just the result of some cosmic accident, surely we could find some attribute that could be improved upon. But when we look at all of the unique characteristics of the Earth that make it habitable, especially after comparing these same characteristics with our terrestrial neighbors, such as distance from the sun, size and gravity, water in all three physical phases, thickness of its crust, rotation rate or day-night cycle, axial tilt, magnetic field, unique moon, and atmospheric characteristics, we quickly realized that to change any one of these essential attributes would decrease the likelihood of life existing or continuing to exist. And even though thousands of extrasolar planets have been detected around other stars so far, with maybe around 1% being rocky planets in their host stars, habitable or Goldilocks zone at the right distance to allow for liquid water, all of the exploration that we've done in space so far has confirmed that truly Earth-like planets across the various attributes we've covered today, which is a much longer list than you typically see NASA addressing. Of course, these exoplanets are far away and we can only detect certain things. But Earth-like planets seem to be truly rare. And all the other planets and moons in our solar system are not even close to being able to sustain life of any complexity. And the other objects in our solar system are essentially barren wastelands. So if we look at just the 9 local design characteristics of the Earth and that we went through and assign probabilities based on their likelihood of occurring in our solar system, where we already have a number of things going for us, such as the right galactic location, the right size and age of star, etc., we can calculate the probability of all these attributes occurring together to be about 1 chance in 50 million. But since they're really about more than 300 finely tuned design characteristics in the cosmos at large, the probability of all of these characteristics occurring together at once is about 1 chance in 10 to the 280th power. So to put that in perspective, there are only an estimated roughly 10 to the 80th atoms in our universe, okay? And imagine that we live in a multiverse with 10 to the 80th universes. Now, all of the atoms in all of those universes together is still only 10 to the 160th power. So we have a better chance of picking one specific atom out of all the atoms in all those universes than we would to get all the finely tuned characteristics of this fine, life-friendly universe just right. So the odds are just incredible against us having all of these attributes come together in one place. So furthermore, most statisticians would say that probabilities of anything less than 1 chance in 10 to the 50th power are not just improbable, but for all practical purposes, statistically impossible. But in any case, to say it's extremely unlikely is an extreme understatement. All right, so this observation that we've just covered is known within the astronomy or cosmology community as the anthropic principle, or sometimes the Goldilocks principle, where everything's just right, or the fine-tuning principle, which is the observation that the universe has many characteristics that seem to have been specifically designed and finely tuned to support life on Earth. And these are some great quotes that I like from some famous secular scientists relating to this principle. Physicist Paul Davies from Arizona State writes, "The impression of design is overwhelming. It seems as though somebody has fine-tuned nature's numbers to make the universe." And the late astronomer Fred Hoyle wrote, "A super intellect has monkeyed with physics as well as chemistry and biology." Out of the mouths of non-believers. And so overwhelming is the evidence of the biofriendliness in our universe that currently the main counterargument to the involvement of some type of creative intelligence is the multiverse hypothesis. And the multiverse hypothesis, of course, speculates that there may be an infinite number or large number of separate universes, each with different sets of physical laws. And perhaps our universe is the only one among all of them to randomly get that set of physical laws just right so that life can exist. And of course, there's no real way to either verify or falsify the existence of additional parallel universes. So the multiverse theory technically doesn't qualify as a scientific argument. And even if we concede such speculation on the existence of additional universes, they all still rely on the existence of some set of orderly physical laws. So where does that order come from? This additional quote from Paul Davies sums it up when he says, "The degree of biofriendliness we observe in the universe seems far in excess of what is needed to give rise to a few observers. If the ingenious biofriendliness of our universe were the result of randomness, we might expect the observed universe to be minimally, rather than optimally, biophilic or biofriendly, life-friendly. Note too that multiverse explanations still need to assume the existence of laws of some sort. So they do not offer a complete explanation of the law-like order of the universe. And finally, invoking an infinity of unseen universes to explain certain features of the universe we do observe seems the antithesis of Occam's razor. It's an infinitely complex explanation."